Okay, so we are going to finish off our lesson on volumes. I've got several examples that I want to work through. The first three that we're going to look at are a continuation from where we left off in class. So we're going to take a look at volumes using the cylindrical shells method. Okay, and for numbers 2, 3, and 4 here, we're going to take the same area and just change the line that we are rotating about. Okay, so we have the area that's bounded between the function y is equal to x and y is equal to x squared, between x is equal to 0 and x is equal to 1. And then we're going to rotate this about the y-axis. Okay, so there's the line y is equal to x, and there's the function x squared. Again, we're going to rotate for example 2, we're going to take that area and rotate it about the y-axis. Okay, so since we're rotating about the y-axis, we're going to draw our thin strip from the line we are rotating, parallel to the line we are rotating about. Okay, so our thin strip is going to be that thin strip that is in red. And know that the distance from that thin strip to the line that we are rotating about is going to be our radius, which is going to be the absolute value of x, which since that is in quadrant 1, the radius there is going to be x. Okay, so if we want to calculate the volume of this solid, the volume is going to be, we pull 2 pi out front. We are integrating from 0 to 1. Again, the radius is the distance from the thin strip to the line that we are rotating about, which is going to be x. And then the height of the cross section is going to be the top curve minus the bottom curve. Okay, so the curve that bounds the area from above is going to be x minus the curve that bounds the area from below. That's going to be x squared. And then the thickness of the cross section, the distance across that thin strip in red, is a change in the x direction. So not only are the limits of integration written in terms of x values, but the functions have to be written in terms of x values as well. So again, if you want to find that volume, you would distribute x across both terms and then integrate term by term. Okay, so I'm not going to keep drawing the same image over and over and over again. We're going to take that graph that we drew up above and then we're going to apply it to number 3. Okay, so number 3, we're taking the area between y is equal to x, y is equal to x squared, x is equal to 0, and x is equal to 1. And this time we're rotating it about the line x is equal to -3, which is going to be over in here. Okay, so a lot of stuff is going to stay the same when we use cylindrical shells here. So the volume is going to be 2 pi times the integral from 0 to 1. The height of that lateral area of the cylinder is still going to be the top function x minus the bottom function x squared. The thickness of the cross section is still a change in the x direction, but what changes is the length of the radius. Okay, so again, the length of the radius is the distance from the thin strip to the line that we are rotating about, okay, which is going to be that segment there in green. Well, we know the distance from that thin strip to the y-axis. We said that that was x. And then what are we doing to that length? We are adding 3 to that length. Okay, so our radius is going to be x plus 3 in that particular case. Okay, let's change things up for the next example. So the next example, number 4, we're taking that same area. This time we're rotating about the line x is equal to 4, which is going to be over in here. Excuse me. Okay, so we're going to rotate about that line. Okay, so again, a lot of stuff is the same here. So we're going to use cylindrical shells. The volume is going to be 2 pi times, we are integrating from 0 to 1. The height of the cylinder is still going to be the top function x minus the bottom function x squared. And the thickness of the cross section is still a change in the x direction. Okay, again, what changes here is the length of the radius. Okay, well, we know that our radius is going to be this segment here in black, which is going to be the distance from the thin strip to the line that we are rotating about. Okay, well, we know that the distance from the y-axis to that line is going to be 4. And we know the distance from that thin strip to the y-axis is going to be x. So that's going to make the length of the segment in black the whole thing 4 minus the segment x. Okay, and that is going to be the length of our radius in this particular case. Okay, so volume is going to be 2 pi times the integral from 0 to 1 of 4 minus x times x minus x squared, which we are integrating with respect to x. Okay, we're going to move through the next example. Okay, so the next set of examples, we're going to take a look at volumes with known cross-sectional areas. Okay, so the first one says to find the volume of the solid whose base is the region between the semicircle y is equal to rad 16 minus x squared and the x-axis, whose cross-sections perpendicular to the x-axis are squares with a side on the base. Okay, so just as was the case with the 3 methods that we looked at prior, so disc method, washer method, and cylindrical shells, volumes with known cross-sectional area, we are still integrating the area of the cross-section, usually with respect to x. Okay, we'll take a look at an example where we don't do it with respect to x later on. Okay, so the good news for us here is, like, we know what shape our cross section is going to be. It's not like disc method or washer method or cylindrical shells where we have to look at our area and the line that we're rotating about and figure out what shape the cross section is, and then use the formula to integrate the area of the cross section. We know what shape the cross section is here. Okay, so again, we want to draw ourselves a diagram. So y is equal to rad 16 minus x squared. That's going to be the top half of a circle centered at the origin with radius 4. Okay, so your graph is going to look something like that right there. Okay, now this says that when we draw our cross sections perpendicular to the x-axis, okay, so I'm drawing that cross section in red. The cross section is a square with a side on the base. Okay, so here's what you have to visualize, because I can't draw this three-dimensionally. But you have to picture that segment in red being a side of the square, like let's say the bottom side of the square, and a square is going to be popping up off the screen out at you. Okay, so what I'm going to do is I'm going to take the square that's popping up off the screen at me, and I'm going to draw that square. Okay, that's my cross section. I'm going to draw that cross section over to the right. Okay, so all we have to do to set up our integral is we have to come up with a formula that gives us the area of the cross section. Okay, well, we know a side length in that square is going to be the distance from the x-axis to our curve, which is going to be the function rad 16 minus x squared. And if we know a side length of the square, then we can determine the area of that square to be the side length quantity squared. Okay, so that is going to be rad 16 minus x squared quantity squared, which is going to be equal to 16 minus x squared. Okay, so if we want to set up an expression to calculate volume, volume here is going to be, now, you have to look at this and figure out whether you are integrating with respect to x or with respect to y, okay? And again, that is dictated by the thickness of the cross section. So the thickness of that like thin strip in red is a change in the x direction. So that means that our integral has to be written entirely in terms of x, okay? So when we look at the area for that solid, the area starts at the x value of -4 and ends at the x value of 4. And then we are integrating the area of the cross section. So we found the area of the square to be 16 minus x squared. Okay, and we just integrate that with respect to x. Okay, so I don't have to like multiply by pi or by 2 pi here because my cross section is not in the shape of a disc or a washer or the lateral area of a cylinder. Okay, but for all of the methods that we look at in this lesson, for all of them to calculate volume, we are integrating the area of a cross section. Okay, let's do number 2. So for number 2, the directions say to find the volume of the solid whose base is the region between y is equal to x squared and y is equal to 4, and whose cross sections perpendicular to the x-axis are isosceles right triangles with hypotenuse on the base. Okay, so let's diagram this one here as well. Okay, so when we draw a picture, we have the line y is equal to 4, which is that line right there. And then we have the function y is equal to x squared, which is this here. So we're taking the area that is enclosed by both of those regions, which is this highlighted area. Okay. And then what we're doing is we're going to draw cross sections perpendicular to the x-axis. So I'm going to do this in red. Is going to be an isosceles right triangle with hypotenuse on the base. Okay. So that's the segment in red. That's going to be the hypotenuse of your right triangle. And then the two legs are going to like pop up off the screen out at your face. Okay, so what I'm going to do here is I'm going to draw that cross section over to the right. Okay, and when we say an isosceles right triangle, that's another way of describing a 45, 45, 90 triangle. Now, the measurement that we know in that triangle is the length of the hypotenuse, and the length of the hypotenuse is going to be the top function 4 minus the bottom function x squared. Okay, so if we want to get the area of that 45, 45, 90 right triangle, we know that the length of the leg times rad 2 is equal to the hypotenuse, which is going to make the hypotenuse divided by rad 2 equal to the length of the leg. Okay, which is going to make the base length 4 minus x squared over rad 2, and it's also going to make the height 4 minus x squared over rad 2. So if we want to calculate the area of that triangle, it's going to be 1/2 the base, which is 4 minus x squared over rad 2 times the height, which is 4 minus x squared over rad 2. So the area there is going to wind up becoming 1/4 times the quantity 4 minus x squared squared. Okay, and again, the thickness of the cross section is a change in the x direction. So if we want to write an expression to calculate volume, I'm going to pull 1/4 out front. And then we're going to integrate from -2 to 2, because that's the x values which enclose that area of the area of the cross section, which is 4 minus x squared quantity squared, which we are integrating with respect to x. Okay, so I'm going to have you guys copy the next two problems down. Okay, so the directions for the first say to find the volume of the solid whose base is bounded by the lines f of x equal to 1 minus x, g of x is equal to x minus 1, and x is equal to 0, and whose cross sections perpendicular to the x-axis are semicircles with diameter on the base. Okay, and then for number 4, you're asked to find the volume of the solid whose base is the region between y is equal to x and y is equal to rad x, and whose cross sections perpendicular to the y-axis are rectangles whose height is 7 times longer than the base. Okay, I want you guys to give those two problems a try. Again, just do the setup only for those, and then we'll pick up with those two examples to start the next video.